Hello everybody, and welcome to this episode of the YoungWonks podcast. Today we're going to be talking about controlling household appliances with the Raspberry Pi. This is a project that a lot of people want to do for various reasons. Maybe they want a lamp to turn on and off automatically to keep their turtle warm, or they want, like a washing machine to start at a certain point and stop at a certain point, or they want even to turn on some other device that then does stuff, like maybe a computer, that only runs at certain times because the power requirements of this computer are high. Sometimes people want to have something where, after a computer is shut down, it's actually cut off from power. So you need some kind of way of controlling 120 volts AC power from purely the pins of a Raspberry Pi. Now, the first thing you have to understand here is you need something called electrical isolation, which means there should be no electrical path by which the 120 volts AC you're controlling can actually reach the pins of the Raspberry Pi, because it would instantly destroy it and also be extremely dangerous. So, to do something like this, we use things called relays. Specifically, in this case, we usually use an electromechanical relay. And what an electromechanical relay is a switch. It's just that, it's a switch. But instead of being operated by you pushing like a slider or something, the switch is operated by the magnetic field from a separate electromagnet. So let's look at exactly how this works. If you are to let's go into drawing mode and draw this out. If you are to have a switch, just a regular one, usually represented in a circuit schematic like this. Electricity doesn't flow when the switch is open, but then when the switch is closed and connects through to here, then electricity flows. So, what you need to do is put like a little magnet, like a permanent magnet on here, and then when you want to close it, you need to create a magnetic field that pulls it down to close it. So, how do you create a magnetic field? You use something called an electromagnet, or sometimes a solenoid. And that is just a long coil of wire, sometimes with an iron core through the middle. So let's go back to the little GIF animation here. As you can see, they've got one of these showing, and they've got a small push button switch that they're actually using to energize the coil. And when that push button switch is pushed down, the coil is energized from the DC source. It creates a magnetic field that pulls down the armature or switch and makes connection between the armature and the contact. Now, the high voltage AC we're trying to control would be connected through the armature and contact and would flow through there. Now, you might ask, well, this thing still requires a switch, right? This doesn't help. The great advantage here is that the small switch you see near the bottom, the push button switch, first of all, it could be a Raspberry Pi or something that doesn't provide, that doesn't need to touch 120 volts. All it needs to be able to do is provide enough current to turn on the electromagnet that closes the relay. It doesn't need to be able to provide maybe the 40 amps or whatever that's going to run your washing machine. It just needs to provide enough current to switch the electromagnet, which closes the contact, which then allows a very large amount of current to flow. Now, a few problems we have to talk about here. And these are sort of the important caveats when you're dealing with relays. The first important caveat when you're dealing with relays like this is something called inductance, the inductance of the coil. In very simple terms, a coil of wire is something called an inductor. And an inductor does not like the amount of current in it to change. So you energize this thing, and it has a very high inrush current, which means it'll draw a lot of current when you first switch it on. Okay, you energize it, it's running, contact is closed, it's good. But then you de-energize it. And what the thing tries to do is it tries to keep the same current flowing through it. Because what inductors do is they don't like the amount of current in them to change. So as the magnetic field in the inductor collapses, and the physics here are beyond the scope of this discussion, but essentially as the magnetic field in this collapses, the current decreases, something called self-inductance happens, and it tries to maintain current through it. What ends up happening is you get an enormous voltage spike coming out of the inductor, which can destroy whatever it's connected to. This is very dangerous if you connect the inductor directly to the Raspberry Pi, so you should never do that. In fact, you normally kind of have two stages here. What you have is some kind of chip from the Raspberry Pi that allows you to switch the inductor on and off, and then the inductor switches the main AC power on and off. So the first chip that you have between the inductor and the Raspberry Pi isolates the Pi from, first of all, having to power the inductor, which might take more current than the Pi's GPIO pins can provide, and second, isolates the Pi from any voltage spikes or too much current being drawn by the inductor. So, how would that look? That would look like this. You've probably seen these at YoungWonks. This chip is often sold for driving stepper motors, but it can also be used to switch relay coils on and off. And all it is like a bunch of transistors and some protection diodes in a little package. And what it allows you to do is, connect up on one side Raspberry Pi GPIO pins, and on the other side a coil from an inductor. And then by switching the GPIO pins, you can switch the current through the coil of the inductor. Then, when you switch the current on through the coil of the inductor, it creates a magnetic field that closes the contact in the inductor and actually causes current to flow. Wow, that's quite a sequence of events that has to happen. But what it gives you here is isolation. There's in fact kind of two levels of isolation. The Raspberry Pi is isolated, not really isolated actually, but it's somewhat protected against the effects of the the coil in the relay, the inductance and back EMF. It's protected from that by the ULN 2003 chip, and then it's also protected from the mains AC because the mains AC never actually touches the entire coil or the Raspberry Pi. It's purely being moved by the magnetic field. So, you might have Raspberry Pi and then you would have a ULN 2003 chip. You might have inputs going to GPIOs. Obviously you need grounds as well. But then you're going to have the outputs going to a coil. And then above the coil you would have the switch part of the relay with a magnet on the end. And this, when the Raspberry Pi takes this pin high here, this caused the ULN 2003 to allow current to flow through the coil. And by the way, you would also have some kind of power connected to the ULN 2003 that's actually, being switched, right? Because the Raspberry Pi is not going to provide enough power by itself. Maybe you'll have a battery, something like that. This causes current to flow through this thing, and create a magnetic field which will pull this down. Now, you don't usually actually build relays yourself, and in fact, if you are controlling 120 volts AC, I would strongly recommend that you never ever try to build a relay yourself, because it's incredibly dangerous if you get things wrong. If you touch mains voltage, it will kill you. So I suggest you get a device like this from Adafruit. This actually has a couple relays on it that you can control. All you do is you plug one end of this, the end of it with the tail, into the wall, always giving it power, and then you plug in the devices you want to control into the outlets on the thing. And then to this little green screw terminal thing at the side, you can connect the signal from the Raspberry Pi GPIO to switch the devices on and off. This thing's a whole lot of isolation, a whole lot of protection. It's really designed to avoid you dying of electrocution. So I highly recommend, I'd say, I mean, unless you really, really know what you're doing, like you're a professional electrician, you do not try to throw together your own relay thing. Now, I also want to address these things. You have almost certainly seen this hat for the Raspberry Pi. I think we used to have one at YoungWonks, or maybe you've seen this one. Never ever use this, okay? And the reason I say this is because you see on the side the screw terminals how you attach or connect the mains AC stuff. You actually have to cut open a mains AC cable and like strip the ends, the 3 wires, and put them in. You'll die if you try this. Don't do it. Get something like this where you don't actually have to cut into or directly interact with any of the mains AC wiring, where you just plug it in and you're good. So, by the way, there was an older version of this thing called the power switch tail that only did one outlet. You sometimes see those around as well, so just be aware that it's a similar device. Now, the next thing I want to talk about is not directly related, or is not strictly speaking to do with controlling the relay, but it's to do with when you should control the relay. And for this, I want to explain the concept of the Schmidt Trigger. So, if you imagine that you have... Well, let's first address the other thing. This thing, the actual switch part of a relay, this is a mechanical device. This is why we call it an electromechanical relay. And the issue with this being a mechanical device is that over time it physically wears out from like clicking too much, from hitting this part. It will wear out, or it will break even. And the reason this is important is that means you need to minimize how much you switch it. Additionally, because this is a physically moving switch, it takes time, like a significant amount of time, from a computer's point of view for it to switch. So you cannot, and you should never ever, PWM a relay. All you'll do is destroy the relay, and it won't even really work, because that's not really how you should control an AC device anyways. Do not PWM these things. You should not be turning them on and off very often. If you're turning them on and off like every half a second, that's like wrong. Don't do that. This is more for an appliance, you know, you turn it on, maybe it runs for 10 minutes, you turn it off. But how do you avoid that? A lot of what people do with these things, they make temperature dependent. They've got some kind of temperature sensor. I'll just label that temp. And they've got that connected to the RPI, Raspberry Pi. There's a really common setup. Maybe they're controlling like the lamp in their turtle tank. I don't know. People make things that take care of plants, that water them, all kinds of things that require monitoring temperatures. They monitor temperature, and then out here they're controlling, you know, that whole thing that I mentioned before, relay. I'm not going to redraw the entire relay circuit. I'm just going to say relay here. Now, what's the issue here? Suppose that you wanted this thing so that if temperature is greater than 5 degrees Celsius, then you want it to turn relay on. And by the way, this is not Python code. This is just like pseudocode to show you what kind of rules are going on here. Else, turn relay off. So, what's the problem here? It seems pretty simple. The relay, which is probably something like, I don't know, to cool down the turtles, maybe it missed them with water, turns on if the temperature is over 5 degrees, and it turns off if the temperature is below 5 degrees. So the thing should make sure that the temperature, gets pushed up. Okay, actually, you know what? Let's do it a different way. Let's do it if temperature is less than 5 degrees, turn the relay on, otherwise turn the relay off. You might use this in a situation where you think that anything over 5 degrees is dangerous and the relay is air conditioning. Say that, okay? Relay, I'm going to put air conditioning there. So this thing should turn on air conditioning, or maybe even refrigeration, since 5 degrees is pretty low, anytime the temperature is lower than... Okay, you know what? Nope, that's wrong again. Yeah, if there's air conditioning, it's for greater. Okay, yeah. Temperature is greater than 5, turn on the air conditioning. Otherwise, turn it off. What is the problem here? Well, suppose that the temperature, and I'm going to draw you a graph here. Suppose that the temperature, lowercase t is time, capital T is temperature. Suppose that the temperature is very close to 5, like does this. Goes up over 5, below 5. Suppose it's very close to 5, and so it's oscillating around 5. Think about what this code is going to do. What's going to happen is right, like, here maybe, where the thing is indeed greater than 5, it's going to switch the relay on. So if I draw a graph of when the relay is on, it's going to switch on here. But then as soon as we get down to here, it's below 5, so now it's going to switch off again. It's off for a little bit, and then it spikes up a tiny bit above 5. Relay turns on again, and you're going to end up with something like this all the time. The relay is going to be destroyed by you constantly switching it on and off. And this is dangerous because it will destroy the relay, and also it's probably not great for whatever appliance you're turning on and off. If this was like an air conditioner or something, it's not going to like it. So, what you need here is to appropriate a concept from electronics called the Schmidt Trigger in order to add hysteresis. And what that means is, instead of having the code say if temperature is greater than 5, turn on, else turn relay off, you need to have 2 thresholds. Okay, you need to have a high threshold and a low threshold. Maybe like 5 and 3. And you only switch the state if it goes past the high threshold or the low threshold. So see what I mean? If the temperature right now is, let's say the temperature was like 5.3, so it's up here, nice up here, the relay is going to be on because the temperature is above 5. But suppose that it, fluctuates a little bit and drops down to 4.9. This is below the high threshold, but it is not below the low threshold, which means, according to the rules of how a Schmidt trigger works, the output doesn't change. Okay? In fact, this thing could go all the way down to here, and the output will still remain on. Let me actually draw that out for you. Give me a sec. We're going to go a little bit over time, but it's really important concept to get in here, so I hope y'all can hang around. By the way, I'm going to do questions in a moment. Okay. This thing is going to remain on all this time. On. This thing, in fact, for it to turn off, this has to drop all the way below 3. Once it's below 3, then yes, this will drop down to 0. But if this thing is fluctuating around down here or even up to here, this remains off. It will only come back on if this goes all the way back over to 5. So as you can see, instead of having like, a constant square wave or like lots and lots of oscillating, this thing only turns on and off occasionally when the temperature is significantly different to what it should be. And that is the magic of the Schmidt trigger. You can implement these as an analog circuit, but in this case, this would just be code. Like, if it's greater than 5, do one thing. If it's less than 3, do the other thing. Otherwise, don't do anything, essentially. All right, now let's take some questions. Give me a moment to take a look at our questions. The formal name for something like this, where you use two thresholds instead of one threshold in order to stop it from, like, you know, constantly switching on and off as the input fluctuates, is called hysteresis. It's a very important concept. All right. So as we can see, podcasts, any questions? Looks like no questions here. So thank you all for coming. Remember, don't ever touch mains AC yourself. You will die. Yeah. Thanks for watching. Be back next week, 6 p.m.